So 4 of us total will each talk for 15, 20 minutes. Leave plenty of time for questions and answers at the end. I think since we have 4 presenters, might be best to save all questions until the end. We promise we'll give plenty of time to answer questions, and all 4 of us will be available for questions. So with that, I'm going to introduce our first speaker, Dr. Steve Shaw. Dr. Shaw is a professor here at SUNY ESF with more than 20 years of academic and professional experience involving hydrologic systems. His projects have included evaluation of pollution generation in urban landscapes, irrigation infrastructure, controls on low flows, channel restoration techniques, and tree water use. Dr. Shaw was a co-lead author for the Water Resources chapter in the New York State Climate Impacts Assessment Report released in 2023. With that, Dr. Shaw, turn it over to you. The clicker is right there for you to advance slides.
Thanks for having me today. So as you can see, I'm going to talk about the New York State Climate Impacts Assessment. Different assessments are done at different scales. People might know internationally, Intergovernmental Panel on Climate Change, IPCC, has done an assessment since the early 90s. The National Climate Assessment has been done in the United States, at least until recently, but I think it's going to be discontinued at least for a while. And then New York State has done this for the last 10 years or so. Right, so the intent of an assessment is basically to have a better understanding of the climate hazards. So what kinds of basic climate drivers, temperature, precipitation, sea level rise can impact your systems, identify sort of vulnerabilities, and then put that together with like where are those impacts really going to happen. In terms of how this was done in New York State, there were basically 7 sectors. You can see what those 7 were. I was involved. I was one of the co-leads for the water resources sector. To understand a little bit what does it mean to do this impact assessment, it was done basically over a 3-year period, and we had a working group to do this. So there are 2 co-leads, myself, another, Kelsey Leonard, who's more of a social scientist actually, between 6 and 8 sector members, depending on the group. And those are sort of specialists in their dedicated areas, and they were sort of the co-authors on the document. And then a 15 to 20 member advisory group from sort of all realms of things. So maybe social scientists, nonprofit groups, engineers, sort of a whole realm of people from diverse backgrounds from the advisory group, and then a peer review, right? So every one of these chapters sort of went through that process over 2 to 3 years. It was, if you look at the chapter, and I'll provide a link later, and you can, if you just Google it, it kind of pops right up. It was a kind of a long chapter. It was interesting. They said don't make it too long, and then in the end, they kept asking us to add things. It ended up being kind of long. So I just kind of picked 4 things that I kind of find kind of in some ways most interesting, and maybe sort of things that people might have preconceived notions about that I find sometimes it's helped to provide some clarity on that. So I'm going to basically talk about these 4 things. What are sort of what may drive change in terms of sort of the climate drivers that may drive change in terms of water availability, how sensitive are different water supplies to changes in availability, what are the risks to infrastructure, and then how might affordability actually be a bigger concern than outright lack of water. So I'll kind of tie those 4 things together. I should say the report itself wasn't structured exactly like this. It was more about sort of water supply, and then in terms of infrastructure and water quality, and then really water treatment in terms of infrastructure and operations. So I sort of mixed some of these different things together. So one thing about this report, different than say the IPCC report that's done in concert with the climate modeling groups across the globe, basically contributing their projections. This report was done without really having new projections from New York State. I would say Columbia did do some projections, but they weren't really available until we were done writing. So what we sort of refer to this as sometimes people talk about a bottom-up style analysis, where basically you're looking at sort of sensitivity of your systems. You're not taking climate projections or climate estimates and using those to try to simulate what is going to happen. You're basically just assuming your system's going to be exposed to stress in some way and looking at sort of where the weaknesses most likely are. One thing though that's informative, and one thing we used in the report was to look at some historic data, right? So what I did here, these are 4 streams. I probably had 4 rivers. Some of the largest rivers in New York, they kind of cover different quadrants. So Hudson more in the east, Susquehanna kind of south central, Genesee sort of northwest, and then Oswego, basically where we are here, draining to Great Lakes. And looking at historical, so this is mean annual discharge. So basically, if you average over a given year, what's that flow rate? Okay, so I'll switch into lecture mode a little bit. Anyone want to make any observations about what you see here in terms of patterns? And I picked 4 just to sort of make the case like we see some consistency across most of New York, right? We sort of see mostly the same thing. But I'm just curious, when people look at this, what do you see? Any thoughts? Yeah.
Drought around 1965.
Yeah, so one big thing that we consistently see, and Scott Steinschreiber mentioned this early on, is we see this drought in the early 60s, right? And that's a consistent part of the signal. We refer to that as the drought of record, basically the driest period in the hydrologic record, the recorded hydrologic record. What is interesting about that is that's useful for us in terms of planning and thinking about this is if you go back, we only have about 100 years of hydrologic record in terms of directly measuring stream flow, but you can have longer paleo climate record, like using tree rings and other things like that. So when people go back and look at the paleo record, they can actually say that that drought of record in the 60s probably only occurs on average every 500 years. So we basically, in our period of record, we have something that is really pretty rare. And that often is what we design for when we design water systems, at least on the dry end. Any other observations about this? Also want to throw something out there? Yeah.
Look at the trends, they all are like have a slight slope up.
Yeah. So there's a slight slope up. But what I'm going to argue, and I'm not quite a climatologist, but what climatologists would kind of say, is that when we look at this and sort of do kind of fancier trend analysis on this on the time series, is that what you kind of see is what's called the step function. So really in the late, basically early 70s, is there's a sharp shift in sort of where the long-term mean is. And what this sort of says is in part, if you believe that, which if sort of more sophisticated techniques say that probably is real, is that this was happening before anthropogenic climate change really kicked in. And what they often deem this as a pluvial. So a pluvial is sort of a climatologist wording for the opposite of a drought, for an unusually wet period. So what we can kind of think about is, from a climatologist point of view, is that there's some amount of natural variability in the climate signal, separate from what's going on with anthropogenic climate change, and we might be in an unusually wet period right now. So what that means in sort of the context of thinking about things is we have 2 ways of sort of thinking about trends. In general, we kind of think we probably will get a little wetter with climate change. Most of the projections say we should get a little wetter. But if we're in this pluvial, this would be the top plot here, is we basically have this sort of unexplained natural variability, this increase in wetness. And just as we went into it pretty sharply in just a few years, we could come out of it just as sharply. So even though long-term the overall trend might be up, it's still possible if we come out of the pluvial, we might actually have a little less water availability into the future. So this is one of these things I will say, like, the climate models don't really reproduce this, right? But having sort of the advantage of hindsight looking at paleoclimate, we know that lots of climate signals, basically, you have a long-term trend and then overlaid over it is this natural variability. So this makes us sort of acknowledge, just like Scott Steinschreiber said this morning, when we look at long-term projections for, say, precipitation in this region, we think we're getting a little wetter, but there's a huge range of uncertainty on that. And part of it is just this idea of, are we in a pluvial or not? It seems like we arguably are. So that's sort of on the water availability side, right? And in some ways, basically what I just said there is we're kind of uncertain about what our future will look like, but it might be drier, not just wetter. The other part of this, what I found interesting that we kind of came out in doing this report is we're going to have warming, increasing temperature, right? So increasing temperature could increase evapotranspiration. But the other thing we see that might actually matter more, and there's a lot going on in this graph, but really what I want people to look at is 2 things, is that the lower line is basically wintertime water demand. This is in Long Island, Suffolk County. And then the black line is summertime water demand. And really the distinction between why is water demand so different between winter and summer? Anyone know why? This is on Long Island. I don't know if there's any Long Islanders here, but anyone want to guess?
Irrigation.
Irrigation, right? And this is the big thing, that the issue becomes like, it's not just what climate's doing, it's what people are doing, right? So there's a definite driver of this temperature, but basically when temperatures go up in certain places, people irrigate a lot more. And the issue for climate change is, well, not only if temperatures going up, maybe you have more evapotranspiration, a little less water availability, but then you also have this compounding effect that you have a lot more demand, which can be controlled, but you have to convince people to change that behavior, which often isn't that easy. So this is a little bit of a theme of a lot of this, is really realizing, like, it's not always just simple as saying, hey, what's temperature going to do, what's precipitation going to do? It's really about what are people going to sometimes do when that happens, not just what the baseline drivers are. Okay, so shifting gears a little bit to sort of the second question of how vulnerable are systems in New York. I always like, I mean, in my mind, I really think relative to other places in the country, we're really not that vulnerable. Like, it's really hard to say that we run out of water. But I think the thing that's important to say is we have a really diverse and fragmented water delivery system in the state. So this is just showing we have maybe 2/3 of people get their water from public surface water, SW surface water, public water supplies, and then about 1/3 from groundwater, where about 2/3 of that groundwater supply are public water supplies, and then a bunch of people from homeowner wells. Within the public water supplies, there's over 1,000 different entities basically operating, managing, and getting their water from different sources. So we can broadly say most people are probably okay. It's totally possible that some systems, because of sort of the size of the system, the people, how they operate the system, are more vulnerable than others. This is one of these things, it's like, well, can you give a number on that? And it's like, without analyzing every system, because every system is unique, it's really hard to do. So this is my like very just back of the envelope sort of way of breaking this out, is I sort of have 6 different classifications of thinking about vulnerability. And it basically has to do with how much storage you have in the system. So you can have on the left-hand side a large reservoir, a large lake, or a large aquifer, and we assume the city is the same size in all these, so demand is basically the same. So our biggest concern is there's going to be a dry period. Do you have enough storage to get through the dry period, right? So some systems like Onondaga County, there's a connection to Lake Ontario. Fundamentally, an infinite supply of water, right? So they're over here like number 1, very little vulnerability. You get to some systems, people don't always realize this, you have run-of-the-river systems. They don't have a lake or a reservoir or an aquifer, they're just pulling water out of a river. If it's a big river, City of Binghamton does this, it's fine, right? If it's a small river, City of Ithaca, they have a reservoir, it's mostly silted in, doesn't actually have that much storage. They're more over by 6, right? And then you get to some of these systems, smaller reservoir, they have some reservoir there, but if it's an extended dry period, say like the drought of the 60s, like lasting 2 or 3 years, they might be in trouble. But every system, in terms of our report, we couldn't assess every system, but hopefully every community, to some degree, is thinking about this a little bit. The last sort of caveat on this is the place where it gets really complicated and you might have the most risk is where you have interconnected systems, especially where they cross state boundaries, because now you basically have politics comes into play. So the one I sort of mentioned the most is to realize that New York City, Philadelphia, and then large parts of New Jersey all draw their water from the Delaware River. If there was a drought on the Delaware River, right now it actually went to the Supreme Court in 1954. There's a Supreme Court decision that said how New York City has to release water to Philadelphia. But you can only imagine what would the governor really do if they had water in their reservoirs and wanted to make sure they could still live up to New York City. Politically, would the governor of New York really say, oh, we're going to just release water downstream of the river? I don't know, right? And that's the kind of thing. And then what you add on top of that is you add sea level rise that would change what's called the salt front, basically the position of salty water in the lower part of the Delaware River. You push the salt front up past the intakes for the city of Philadelphia. So you have not only water availability issues, but interacting with sea level rise and then the politics of all that. It's sort of one of those black swan situations, right? It's probably really rare if it happens, but if it happens, it's going to impact 20 million people in terms of how that plays out. Right. And it's one of those things people are thinking about a little bit, but it's not like there's one person or not, there's not like there's 10 people who have constructed this model to understand this really well. And there should be probably, but that hasn't happened yet. And this was just to give a sense, one more slide, but this is showing the degree of management that's already going on in the Delaware River. So all sorts of different pools and sources and reservoirs that can be released. So already a really complicated system, but that just sort of shows like, you know, how complicated is it to manage these things, especially across state lines. And then you throw in climate change and you throw in a really dry period, it gets really complicated. Okay, moving on. So my third point about infrastructure. So one thing, especially even on the water supply side, even if we sort of say water supply, we're probably not likely to be that much drier. We are probably more likely to have more floods. And floods can still affect water supply in terms of our water supply infrastructure, right? So I don't actually know, this was just a nice slide I found on Google Images. I'm not sure if this is a water supply reservoir, but it looks probably like a lot of other ones do. But basically, right, if you have a big flood, which you're probably more likely to have, and you damage your water supply infrastructure, that in itself can then threaten your water supply. And especially then you add on aging infrastructure, a lot of these dams are beyond the point of what they need to be for repair, and you have a risk there. the same thing happens, I'm gonna switch gears a little bit now to water treatment side. The same thing is true for water treatment, because we often think of how is water treatment sensitive to climate change. It's most sensitive in terms of damage to infrastructure. So most water treatment facilities are located at low elevations because they want to be near the point of discharge for effluent, but also because most conveyance is by gravity. So you want to be at the low point of your system. So that often puts water treatment systems near the shoreline, whether it's the ocean or a lake or a river. This was the Bowery Bay wastewater treatment plant in New York City, showing, this isn't showing actually inundation during Tropical Storm Sandy, but different floodplain estimates for different years. But you can basically see most of the plant would be underwater. So what does that mean? Does that mean you can't have a plant there? Well, what it really means, and what New York City did post Sandy, is basically say, we can do lots of things engineering wise to address this. So we can elevate critical equipment, we can flood-proof certain critical pumps, we can install barriers to keep water from entering. But then the key piece of that too, if you see on the right-hand side there, is it all costs money, right? So this comes back to a lot of our issues in climate change. It's not like we can't address them, but it starts to cost money to address them. So switching back just gears to water supply side. So one thing we often talk about is, how will climate change affect water quality? There's strong evidence that as water temperatures get higher, so sort of the magic threshold for algal blooms for cyanobacteria is somewhere around 24, 25 degrees Celsius, right? So this was a Wasco Lake. Probably would have been nice if this data went back further, but I think this sort of shows like 2014, you have some indication of blooms, but not that many, but then you start to get more frequent observations as we get further along here. And I think as we go further in the future and you watch temperature go up, you're going to see more of that. That's not to say the city of Auburn can't use that water, but they had to install granular activated carbon treatment, right? So it's not that this says, no, city of Auburn has no water. It just means it's more expensive to have water, which kind of gets to my final point. This is from economists looking at prices of things, that the cost of water and sewer has basically been outrunning consumer goods in the last few decades. I don't know if this is all due to climate change, but that's just the trend they're seeing. So if you basically look at water affordability, right? What can the average person afford? So based on prices compiled, so average cost per household, this is per month. So City of Syracuse, around $45 a month. This is from a few years back, probably a little higher now. New York City, $65 a month, right? So 12 months, that's your average household expense. EPA's affordability benchmark is 2% of annual household income. If around 20% of the lowest income households are only around $30K per year, right? 2% of $30K is $600 a year. You're basically already at that point where you have water affordability issues, right? So this is, especially for me as an engineer doing this assessment and working with social scientists on this is one thing I didn't think about that much, right? But really, it's like when we come back through the study and say, it seems like the bigger issues, we can engineer our way out of a lot of stuff. But in that process, are you basically pricing people out of making hard decisions? I'm going to pay my water bill, I'm going to pay for something else, right? So those are some of the issues. Like a lot of these things, it comes down to, where do we put our resources? Do we need to subsidize water for lower income people in the community? Yeah, maybe we do, but I don't think we fully thought through that yet. Okay, so quick conclusions. Let's see, long-term future water availability. Well, probably water. There's still some uncertainty around that. Demand changes might be driven, so increases in temperature might change demand more than it really changes supply. And water supply is highly fragmented, lots of different systems. To really sort of understand risk, you have to understand each of the systems. So it falls upon communities in a way to basically try to make sure they understand that they have a reliable water supply. And then the last thing, sort of as I've been saying, we can engineer our way out of most of this, right? But that basically has costs and other implications, and you have to make sure you're kind of accounting for the social costs of doing that engineering. Okay, on there. Any quick questions that anyone's got one quick question? Or we can save it. No. Okay, we'll keep moving. Right.
Thanks, Dr. Shaw. Want to very quickly introduce Dr. Chuck Kroll. Dr. Kroll is the current director of the graduate program in environmental science at SUNY ESF and has specialized in civil and environmental engineering for more than 30 years. Over the course of his career, he has served as the chair of the Environmental Resources Engineering and partnered with the USGS, EPA, NOAA, NASA, and USDA on research. Currently, his research interests are in environmental modeling and management with applications to water resources, geospatial, and ecological engineering. Go ahead, Dr. Kroll.
This is my clicker.
Yes, yeah, and if you speak over there, that's what
Okay.
Thank you.
Thanks for being here. Steve recently asked me if I would come and talk a little bit about droughts, and so I'm going to give you a little information about droughts today. So I'm just going to sort of give you an idea of what I'm going to talk about. I'm going to talk a little bit about just like what is a drought, how do we define drought, some tools, very common tools that we use for drought assessment. Going to look at two recent sort of drought scenarios, the 2016 drought in New York State or in the Northeast, as well as just this last year, and some of the ramifications of that, a little bit on climate change impacts on drought, coming from Steve's report, and a little bit on some of my ongoing research on drought in New York. So here we go. So drought is really just a deficit in water from what we really expect. So a drought that impacts, let's say, Arizona is going to look very different than a drought that impacts New York State. But so it's really like relative to what we expect that we're going to see. It's complicated. There's a lot of sort of factors that do this. It's difficult to monitor. It's difficult sometimes to define. It often has a longer time frame than other natural disasters, right? You think a flood comes and we know when it comes and when it ends. Droughts can often happen, even with flash droughts. Shorter droughts often occur over a series of weeks, and longer term droughts can often be a series of years here. Ashokan Reservoir right here last November was at 60% capacity. Typically, it's not full in November. It's typically around 80%, just under 80%, but you can see capacity was lower, and we'll talk a minute about what caused that. So drought, obviously is a reduced water availability. It could be just, it's normally driven by a precipitation deficit, but then the ramifications are often much broader than that. There's economic losses to droughts. Very often it's agricultural based, but it could be from that, prices changing, things along this. It's often a time of ecological stress. A lot of times low flows in rivers happen in, let's say, the late summer. Dissolved oxygen concentrations are lower than in our streams, and these can be times of increased sort of stress on both terrestrial and aquatic water bodies. We look at 2013 here. This comes from the American Farm Bureau Federation, just sort of looking at crop losses. They lumped in here drought, wildfire, and heat. Wildfires tend to often happen during droughts, right? And we look at the wildfires that have happened out in California, or even the ones that happened downstate last fall, driven by a drought sequence. You can kind of see here the estimate over $16 billion in losses in 2023. Texas alone, about $4 billion in losses. So it's a pretty big impact, depending on how you look at this. And so back in the early 2000s, Congress was looking for a more coordinated effort to both define drought, respond to drought, and ideally forecast drought, though we really don't do that well. This led to, in 2006, the pass of the National Integrated Drought Information System, or NIDIS, Act of 2006. And so from that's actually been reauthorized twice, I believe in 2014 and 2016 or 17. But one of the things that it created were what is commonly referred to as DEWs, drought early warning systems. And so where we are here in New York, we're part of the Northeast DEWs, which is basically of New England and New York, right? And so those DEWs basically coordinate an assessment of drought within each of the regions. There's regions throughout the whole country. And one of the tools that they work on a lot is called the US Drought Monitor, or the USDM. And so that map up there, I'm going to talk about in just a second, that's the current drought monitor. So the drought monitor comes out every week. It's a weekly assessment. Let me go back here. It's a weekly assessment. The maps are basically every Tuesday. They're developed and then they're published every Thursday. And so lots of things factor into this. There's lots of sort of potential indicators of drought. Obviously, precipitation is an important one, but they also look at things like low soil moisture, stream flow deficits, groundwater levels, also things like reservoir levels. So we talked about Ashokan just a minute ago, vegetative health, snowpack. So there's lots of different factors that sort of go into, are we really in a drought here? And so developed weekly by a combination of NOAA, the USDA, and the National Drought Mitigation Center, which is out of the University of Nebraska. It blends both those physical indicators, but what's also important is that it really uses local expert knowledge. So they're a group of people. It's, this is one of those things where it's doubtful that like AI is going to take over this, right? It's not something that's typically automated, that they look at a lot of different indicators of drought, and then a group of people sort of determine sort of what the different drought categories are. They sometimes talk about this as a convergence of evidence approach, that they're looking for multiple indicators of defining where a drought may be. So this is the current map published last Thursday for the United States. Okay, you can see the different colors, the very pretty map that happens here, and the colors have meaning to them. And so you can kind of think, I put these percentages along the bar at the bottom to give you an idea of how they do these. And so you can kind of think, if you have like, let's just think about precipitation. Let's say you've got a record of 100 years of precipitation for that period. It might be just the last week or a longer period. They look at 90 days, all the way out to 90 days, and sometimes even longer with this. And so the idea is that if your current condition is like smaller than the second percentile, then you're in D4. Right, that's the darkest color that you have. So you can kind of think 2%, like in that, it's like a 1 in 50 year occurrence sort of thing, right? You can kind of see that the none is like 70% of this. And so to get in here, you gotta be below the 30th percentile. That's sort of where D0 starts. And then D0 goes from, you kind of think from 30 to 20, D1, 20 to 10, D2, 10 to 5, D3, 5 to 2, and so finally the biggest sort of drought category, the most extreme, is D4. You can see Texas right here. Mentioned Texas in the last slide, 2023. The drought in Texas has been going on since 2021, right? It's like we're talking 4 years of almost continuous drought, especially in western Texas. So this is like the current map that you can see we're looking pretty good in the Northeast, though we weren't too long ago. And so the most sort of in the last 10 years, the most extreme drought that we've had was 2016. You can kind of see this sort of map, and you can kind of see this red area. So we're D3 in western New York, sort of the Genesee River Valley that happens right here. But this was a pretty extensive drought that happened across the entire Northeast. You can kind of just see from the color scheme that goes here, most of the Northeast at this, and this is September 13th, so it was in the middle of this drought period. In New York State, where many farmers do not have any irrigation, right? That's one of the common things. We're a relatively water-rich state. 70% of they did a survey. It was about 250 farmers responded to this. 70% indicated that over 30% losses to their crops during this, right? Pretty substantial. Those who had irrigation also had losses, right? So in western New York, for fruit and vegetable crops, irrigated crops over 30% losses, right? And so, well, they're irrigated. Well, there was two things that came out of this, and sometimes you need a disaster to sort of, or problem like this to show the deficiencies in your system. One, the irrigation systems were often inadequate, but two, you need water to irrigate, right? So the source of that water, even if you have an irrigation system, there are times when the sources of that irrigation aren't available, right? Which causes losses like this. So let's just quickly look at this last year. So what I have here is like a 3-month going right to again last week. So you can kind of think May 13th was just last week, but then we go in a 3-month stretch. So you can kind of see sort of an evolution of drought that's happened in New York State in the last year. And so if you go back to last August, things are looking pretty good, a little bit in sort of southern New Hampshire. But then all of a sudden you go just 3 months later, November 12th, right? What happened? Well, September and October were unbelievably dry. In Central Park, where we have 156 years of record for precipitation, which is a huge record. September had, I believe, 1.58 inches. If you looked at the historic record, this was about the 15th percent, so the lowest, right? So, and then October, 0.01 inches of rain in Central Park, the driest month ever in record, right? Those two created a drought. So, it's not like you need years of dry periods for a drought to occur. Like, this evolution can happen relatively quickly. The end of November got some precipitation, but before that, there was a drought warning. So there's sort of like there's a drought, what they call a drought watch, then there's a drought warning, and then there's a drought emergency, right? And so the drought emergency is often when people are forced to reduce consumption, no more washing your cars or watering your lawns and things like this. Typically during a drought warning, they're looking for like people to try to reduce their usage some. And again, I mentioned the fires. New York City had more like brush and wildfires than they had ever seen in their history, right? Drier conditions often lead to fires, right? It's one of those things. Started to come out of this in basically in December. They called off the warning. We were actually, I just shown like a month ago, things were pretty dry. I know I'm a gardener. It's been a pretty wet month we've just had, right? And so the idea here is that like a good, few weeks of rain can pull us out of this system. And you can kind of see now, last week, there's still some dry things here. I think that's Queens in Wayne County, low groundwater levels are causing that. Downstate, a low precipitation over time in like Rockland, Orange, and as well as in New York City. And so you can kind of see that droughts evolve over time and their impact also changes over time. So another thing that I just want to like point out is the Northeast Dews dashboard. This is published out of Cornell, the national the National Regional Climate Center. This is an incredible resource. If you're ever really interested in sort of drought conditions, I just showed you the main page. Each one of these is like a drop-down menu of figures, right? And you can look at precipitation patterns, soil moisture patterns, groundwater levels, stream flow, right? All of these different things. Almost all of this data comes from point measurements, so that's an important thing to sort of think about with drought. A lot of these are just like, okay, I measure it here, but what does that tell me about my whole system? And I'll talk a little bit when I talk about some of the research projects that I'm working on, how we're trying to address this. But you can see evaporative demand and soil moisture. A bunch of different things. So if you're ever really interested, sort of what are the current conditions in terms of drought in my area, you can go right up to this page and see this. So Steve was involved in the New York State Climate Impacts Assessment. So what did that report say about drought? Well, it basically said there's a real potential for an increase of short-term seasonal droughts. Weeks to months is sort of the thing, especially in the summertime. The expectation is more intense precipitation with sort of longer dry spells in between these, right, which can often cause drought. Higher temperatures in the summer, also causing drought, and the potential for reduced snow cover. If we have a warming atmosphere, reduced snow cover, exposes soil sooner, more evaporation of that soil. The thought of this report was that long multi-year droughts are not expected to increase. Multiple people, including Steve, has talked about the 60s drought. That was a 4 to 5 year drought. We haven't really seen that again. It's generally been like a smaller time period, but it's certainly possible. And the impacts of that would be really extreme on agriculture throughout the Northeast and in New York. So real quickly, I just want to talk about two different like research projects that I'm working on or I've recently worked on, trying to like address this issue of drought in New York State. So what I'm doing here is some modeling of a thing called the National Water Model. It's based on a thing called WRF Hydro, the Weather Research and Forecasting Model. This is a fully distributed model. One of the motivations for pursuing this is, like I said, we only have these point estimates of soil moisture, precipitation, stream flow. The idea is that if we can potentially model this in a distributed fashion, we can get more aerial like sort of understanding of what's happening. And so this plot over here on the left shows soil moisture. The National Water Model is the purple. And this is again the same 2016 drought. So September 13th, same map that I showed you before. And the green line is from the New York State Mesonet, another great resource that we have in New York State, comes out of the University of Albany. Basically, every county has like sort of a slightly advanced weather station, often with soil moisture, soil temperature, obviously precipitation, and other meteorological variables. And what we were trying to see is whether we could produce the soil moisture signal. I will say that the National Water Model actually does a pretty poor job in soil moisture. It actually does a much better job, we saw, in reproducing stream flow. But what we were trying to do is look at this, and where this is really important, and I should have mentioned this before, is defining the regions of the drought, especially between D2 and D3, is critical to farmers. If you are in D3, you get the availability of lower cost federal loans. So where they draw those lines between the different categories, if you're a farmer, matters a lot to you. The cost of that loan goes down substantially, right? And so there was a lot of discussion about in here, you can kind of see we're out in D3 in Western New York, but if you happen to be a farmer that was hard hit just on the outside of that line, you were paying more for your loans to try to make up for this, right? So we're trying to think about, like, can we use models to help us better understand the extent of these drought categories? My time here. So another experiment that I'm doing, and this is actually was partially supported by the Center of Excellence. We're looking at doing some modeling in the Catskills in New York City's water supply. This is on Schoharie Creek, so it's flows into the Schoharie Reservoir. A ungauged, unregulated stream, so we often like to work on those so we don't have to worry about anthropogenic impacts on this. And what we're trying to do here is see, a lot of times when we like calibrate a model, so calibrating a model is when you're trying to essentially tune the parameters of the model to fit your observations. A lot of times you use daily stream flow. That's a very common thing. What we're trying to see is, well, what would happen if you increase the averaging period? The thought here is that a lot of times these models, when you work on a daily time step, are really tuned to try to capture the biggest flow events, the floods. And could we potentially capture, low stream flow processes, groundwater recharge and discharge better if we use a longer calibration period? And so what we did was, along the here of those plots, I've got basically bias and root mean square. Bias you want as close to 0 as possible. Root mean square you want low. So we're comparing these, and we're looking at how well we sort of estimate annual low flows, 3, 7, 14, and 30-day low flows. Why those? Well, typically, for a kind of a low flow hydrologist, part of me is a low flow hydrologist. Anytime someone, National Pollution Discharge Elimination System permitting, you need an estimate of some low stream flow statistic. Typically, it's a thing called the 7Q10, the 7-day low flow with a 10-year return period, or a 30Q10. And so we were trying to look at how well we were going to capture these. And you can kind of see that at this site, when we're basically in here, we go from like a 1 day averaging period up to a 30, you can kind of see we hit a sweet spot here around 14 days, improving our estimation of this, right? So related a little bit to what I was talking about with droughts. And so droughts are hard to model. Like I said, a lot of hydrologic models are like tuned in to try to capture flood events. Often groundwater processes are very simply represented in those models. They're often an afterthought you can kind of think of, but it's what's really driving sort of the drought series. And so we're trying to look at how we can improve that from a distributed modeling perspective. So acknowledgements, I want to acknowledge, I should have had a picture. I saw Scott had pictures of those guys. I should have my picture of. I definitely want to give a shout out to Tom Wan, a recent PhD student. She has worked closely with me on this work. This work was funded by NASA, as well as some gap filling that I got from the Center of Excellence, which I appreciate, as well as SUNY ESF. So that's all I have. I'll be happy to answer questions now or at the end, like our convener said. So thank you. Am I done? Okay, thank you.
All right. Dr. Zach Berdor is a postdoctoral associate in the Department of Biological and Environmental Engineering at Cornell University. Dr. Berdor completed his PhD at Cornell in 2023. His research focuses on forecast-informed reservoir operations and other approaches for applying risk assessment strategies to water resources planning. This is well backwards. I think it should be.
Awesome, thanks. It's awesome to be here, and I thank Steve for inviting me. Also on short notice, like Chuck. But actually, yeah, this is really cool and a cool opportunity to give some flavor to the work that I do on using forecasts for water resources management type stuff. I want to thank the folks that have helped along the way with this work. Of course, Scott. So hopefully a lot of you saw his presentation this morning. I still work for Scott, as well as a bunch of other folks across various agencies listed at the bottom. So I'm going to talk today about hydrometeorological forecasts, mostly talking in the short to medium range, so like the weather time scale, and how they can be a climate adaptive strategy for water systems. Just a little background on me. I've had kind of an interesting career path to being a postdoc. What I'll say in a nutshell is I have a lot of real world experience dealing with forecasts as a former pilot, and but as Matt said, I recently have been doing the water resource engineering thing. So when we talk about water resource systems in a broad context, if we talk about, so to give you a little bit of prelude to what I'm going to talk about today, my work is largely centered in the Western United States. So I'm going to talk a little bit Western focus for a bit, but at the end I'm going to come back to sort of the New York relevant potential applications of this forecast informed water management idea. So when you talk about a place like the West Coast, there's this standing challenge of very high interannual variability that always makes water management kind of a challenge. And when we talk about things like climate change or whatever we want to say these days, climate variability, what have you, the things that we used to consider extremes now more normal, and our extremes are getting worse, which creates even more challenges. Steve already alluded to this challenge. We have tons of aging infrastructure, and many of our major dams and major infrastructure are super old, so they've probably passed their intended service life, which makes them vulnerable to climate change. But on the kind of opportunity side, and where I'm going with this, is that when we talk about forecasts, skill of our forecasts has actually increased steadily over the years. And you can quantify it as a kind of rule of thumb of like 1 day of lead time per decade and increase in skill. And so in a concrete sense, what that means is that a 4-day forecast today is basically equivalent to a 2-day forecast in 2000, for instance, which will come up later in an example. Another really promising innovation has been ensemble forecasting, which has become sort of the the predominant approach in a lot of the water resources engineering contexts. On the stakeholder and practitioner side, there's still some reticence to actually adopt it, but I think the needle's starting to move. So there's definitely an opportunity there. And so when we put these opportunities and challenges all together, we get this idea of forecast informed water management kind of in the center. And of course, underlying all this is the people problem. We have all the institutions and the stakeholders and everybody who actually have to see these this paradigm shift in water management be implemented. And you could view that as either an opportunity or or a challenge. It's an opportunity in the sense is that when people start to understand what forecasts can do, they can get really excited about it. It's a challenge in the sense that things like uncertainty are not easy to communicate to folks that aren't familiar with probability statistics, for instance. And so I'm going to come back to some more specifics on the work that I do, which is this idea of forecast informed reservoir operations, or FIRO. And so this idea has a long application, or sorry, has a long history in the research. And so like folks like Jerry Sedinger have been doing FIRO stuff since like the 90s, potentially earlier. But what we're really seeing, in the last 10 years or so is a push for real world implementation. And this is coming from that sort of coalescence of improved forecast skill and really a strong need in our water system to have better management solutions. And so this quote here is from Marty Ralph, who's director at the Scripps Institute of Oceanography, Center for Western Weather and Water Experience, has really been pushing this strategy as a very powerful climate adaptation management technique. So FIRO is now officially defined as like 2020 in the American Meteorological Society. And you can see it below. You can think of it as FIRO as standing for forecast, but it also can stand for flexibility. We want to think about how we operate our water systems in a more flexible way. Importantly, it's a soft water solution, which means we don't necessarily need to change infrastructure to reoperate our reservoirs. We just need to change our operation strategies. And then a lot of FIRO is really kind of in this dual role of like trying to increase water supply while continuing to manage flood risk via the use of forecasts. So to get a little taste of what FIRO looks like, on the left side, you see the kind of legacy water on the ground type operation of the reservoir. So in the flood season in Reservoir X, you have to draw the water way down. So in case the flood shows up, you have all this volume to catch those flood flows and then release them over some period of time. With FIRO, we can think about that flood space a little bit differently because we're now using forecasts within the construct of our operations, potentially giving us more opportunity to store more water to get us through, maybe a following drought. And so I this fun little animation courtesy of someone I work with, Chris Blaney at Snowball Water. And so with our legacy operations, again, we have to draw the water way down during the flood season. With FIRO, we can actually leave the water level much higher because we're using forecasts. And so we can look out and we can see a forecasted storm event. We can execute what's called a FIRO pre-release. We can draw the reservoir down, giving us space to capture those flood waters. And then when the storm comes, it'll fill the dam back up. If we had a good forecast and a good response. With our legacy operations, as soon as that water fills up, it's got to be let go again. But with FIRO, we can actually keep the water at a higher level, which can again allow us to weather these droughts that Chuck was talking about. So our work has been part of a formal effort to implement FIRO largely in the Western U.S. now, but as I'll talk to in the following slide, with intent to expand it across the U.S. And so it's led by the U.S. Army Corps of Engineers. It's gone through 3 phases, so we're in the 3rd phase now. The initial phase was what they call a pilot study, which was done at Lake Mendocino in California. They subsequently phase 2 looked at a smaller subset of sites. And now in phase 3, it's really looking nationally to try to expand this effort again across the United States. What's really cool about the FIRO project is this very tight coupling of research, operations, and practitioners to really try to figure out how we can make these effective decision-making tools that are using uncertain forecasts. And one really impressive thing that this project has done is try to address this people problem. And so for each of these projects, they put together what's called a FIRO steering committee, which is a group of stakeholders It could be, federal folks, state folks, local folks. Get everybody in the same room together and come up with a plan for how they're going to implement FURO at their reservoir of interest. And so, as I mentioned, as this project moves forward, the intent here is to expand this further eastward. So again, a lot of stuff been done in the west. Today, some of these are still kind of in their planning phases, not implementation yet. But again, the idea being where there is a promise for FURO to be implemented, we should think about doing it. And it actually works. And so so this is a pilot site like Mendocino, and you can see whatever. The orange line is a kind of a legacy flood curve. The gray line is the new curve with forecast informed reservoir operations. And so they can allow that water to go up that line, and it gives them a significant amount of extra storage to weather, potentially dry periods that would come after. And you can quantify that, the number of homes that have better water supply reliability. So I'm going to touch briefly on some of the work that I've done in this space, and then I'm going to go into some potential New York State applications. So my primary work in this space has been in the area of robustness and resilience of FURO policies. And so one of the challenges with FURO is that when we train, design, and operations policy for a reservoir, we're relying on hindcasts, which are typically only available in a very short period of time, so about 30 years, which coincides with the satellite era, and where we can run these very, very computationally complex forecast models. But for the design of water systems, we'd really like to be able to capture forecast operations, where we have observations available. So in that pre-hindcast period, back to maybe the 1900s, if you will. And certainly we want to know how our policies are going to perform under climate change. And we can't do that with the current hindcasting technology. So this is where this idea of synthetic forecasting come in, which is been a big part of what I've done in my PhD, and I'm still working on in my postdoc. And in a nutshell, synthetic forecasting is an algorithm that is a statistical algorithm that can mimic the skill in the hindcasts and propagate that anywhere we have streamflow observations available. I say observations in quotations because it really can be any streamflow source. So it could be a projected streamflow trace. And so if we can do that, we can now generate many, many samples of plausible forecast sequences stochastically and assess our policies across a much richer set of data. And that's the basic idea. We can do this both in the historical record and also, potentially under climate change scenarios. And this gives, going forward is one of the really exciting possibilities here to couple this with other stochastic techniques to generate scenarios under climate change. We can play around with the skill of the forecast, understand what the impacts of improved forecast skill or degraded forecast skill, in this kind of like digital twins type scenario generation, which is some work that we'll, that we're working on right now. So let's go into some potential applications in New York State. I'll start off here. Scott already talked about this morning for folks who were there. The St. Lawrence, Lake Ontario St. Lawrence system, they use seasonal forecasts there. So a much longer time scale than I'm kind of talking about in what previously. But all this highlight that they are using forecasts to inform the operations of this very large system. And so one can, infer that as if we're able to improve seasonal forecasts, which has been a challenge, there's a potential benefit to operations as we think about, changes to that system under climate change. I'll thank Steve for this recommendation. So one I wouldn't have thought of is the Oswego River system close to home here. There's a water management challenge here in the sense that all the highlands off the Appalachian Plateau, when you get a big regional rain event, it can push a lot of water really quickly into the lakes like Hugo Lake and Seneca Lake. The problem is there's this trough where the Seneca and Oneida rivers come together where water kind of pulls up and can create a lot of flooding problems. And so you have a challenge there in terms of water management. You have a people problem. There's a lot of disagreement about how we should manage the system. And then from this earlier report from the 2000s, they said, well, forecasts might be useful, but they're not useful right now because they're only good out 2 days. Well, as I mentioned at the beginning of this, these forecasts might be closer to 4 days now. Maybe that gives us enough time to actually do something useful. And then the last one that Steve already mentioned is the Delaware River Basin System. So as mentioned, New York reservoirs have some legal requirements to support flows in this system. Particularly important is this trend requirement, which is not a legal requirement, but is necessary to prevent, in certain years, to prevent the salt front incursion problem. So again, going back to this 1960s drought where this happened, we want to prevent that happening. And this is a place where FERO might have a possible implementation because there are some pool reservoirs within the system that are basically run of rivers. So it's, can we use FERO to help out with this problem? So with that, I will close it out, and that's what I like.
We're doing pretty good on time. I will talk quickly. Get down to my stuff down here. I'll talk quickly and whoops, that got cut off a little bit. Leave plenty of time for questions for the four of us. Once again, I'm Matt Pacheco with Corollo Engineers. I'm part of Corollo's Resilience Management Group. We focus on infrastructure for the water, wastewater sector. So I'm going to give you a little bit of insight into how these climate change considerations play out in kind of large water infrastructure projects. We've kind of talked about the primary challenges to water resources from climate change, changing drought frequency and intensity, more prevalent algal blooms and cyanobacteria and water quality issues from that, and more frequent and intense extreme precipitation events, which can manifest in a variety of different vulnerabilities to water infrastructure, whether it's direct facility impacts via flooding or runoff and water quality issues. And I'll kind of talk through a couple examples of that. The main thing to keep in mind when talking to engineers like myself is that we hate uncertainty, right? You give me set design criteria, I'll design to that all day long, I'll be happy as a clam. But you add in these kind of changing future design points and things get really complicated really fast. And I always like to start by talking about the primary cause of uncertainty when we talk about climate change, which is uncertainty in future emissions and uncertainty in future change. We often plan water infrastructure projects to operate for decades and decades and decades. And you look at these greenhouse gas concentration pathways, you get out to 2060, and there's actually quite a significant variance in the pathways that we could take, and that manifests in different amounts of change. So how do you design a water infrastructure system in 2025 that can operate under a variety of future conditions? It's certainly a challenge. We'll talk about a couple examples and strategies to kind of manage that uncertainty. But I think the conversation that we've had so far here today has gotten at the main issue, which is it's often not an engineering problem, it's often a financial problem. It costs money to design to these things, and how much uncertainty do you plan for? How much risk are you willing to tolerate, especially into the future? One thing I did want to mention, it came up, I think, a couple different times, but the drought that we saw this past fall in September, October, November had pretty significant implications for water resources in the lower parts of the state, and New York City in particular. New York City DEP, which is the water utility for the city, was in the middle of a $2 billion project to fix leaks in the Delaware Aqueduct. The Delaware Aqueduct brings water from that combined Delaware River system that I think we showed, I forget who showed maps of it, but we saw a map of the Delaware River system. That's the tunnel that carries that water to New York City. It's actually the longest tunnel in the world. And it's leaking. It's been leaking for decades now. And the final phase of this project was supposed to begin October 1st of last year, or did begin October 1st of last year, when this section of the aquifer was shut down. And then, as we've kind of shown, the drought was so significant that 6 weeks later they had to postpone the project and reopen the aqueduct for a variety of reasons. There's a concern that water availability would be questioned going into the city. They're also concerned about releasing water to the other users of the Delaware River. They had actually drawn down these reservoirs pretty significantly in anticipation of this shutdown because they wanted to allow them to fill back up in the 9 months that this aqueduct was supposed to be offline. And that created a real issue with Philadelphia and Trenton, and there were political kind of considerations to the city having to release this water, but they didn't have a ton of water to release downstream because they had purposely drawn it down for this project. And I was teasing Zach a little bit when we were talking earlier about his forecasting models because DEP did utilize multiple independent but longer range forecasts to try to pick the right time to do this shutdown. They used the NOAA drought forecast, which Chuck talked about. They contracted the Columbia International Research Institute separately to perform their own analysis. And they determined a set of decision triggers, rainfall through the summer, through September, stream flows, reservoir levels, both on the East Hudson and West Hudson sides. And all of those triggers lined up quickly, and they had a go, no-go decision, and they made that decision to go. And then, this monthly drought outlook that was valid for October, which showed, no drought in the Northeast turned into that. Right, which is kind of what we've talked about, significant drought in that area. But what they did intelligently is they also predetermined bailout triggers. They said, okay, if we don't get X amount of inches of rain by November 1st, by November 15th, we have to pull the trigger and delay this project. Otherwise, we risk significant issues. So while this does have very real implications for this project, it had financial implications for the city, there were no greater public health consequences because they had planned ahead for not only when to make this decision to start this project, but also how to bail out of it in a timely manner in order to preserve water resources. So that was just one example that I thought was worth mentioning because we talked about that drought a little bit, and it did have a very significant impact. I wanted to show just a mini kind of case study about a water treatment project that I'm working on, that Corolla is working on. This is the Alejandro water treatment plant in Nashville, Tennessee. And the reason why I want to talk to you about Nashville, Tennessee, even though we're here in New York, the issues are pretty similar. The climate change risks are similar in Nashville. Nashville is kind of like a hotter, slightly wetter New York. So what we see in Nashville is probably a decent analog to the change that we might see here when talking about water resources. And Alejandro was the first water infrastructure built in the city of Nashville. The George Ryder pump station was completed in 1888. It supplied raw water to the city for fire prevention. The first treatment infrastructure was built in the 1920s, pre-treatment and filters, and the last major expansion of this plant was in 1960. So this is talking about aging infrastructure. This is it right here. This facility has done a great job, supplying the city of Nashville with water, but is not equipped for kind of what we expect to see in the future. And the city has recognized the need for significant renovation of Alejandro. This is what it will look like in the future: new raw and finished water pumping, new pre-treatment and filters, and GAC, which I think actually Steve mentioned, GAC contactors, granular activated carbon. We're going to talk about how climate resilience is kind of built into this treatment plant expansion and what the gaps in knowledge are and how we're trying to address that. So one way we talked about extreme precipitation, river surge flooding is a huge issue in Nashville. These are two pictures of the treatment plant from the 2010 flood. Those buildings are not supposed to be underwater, but this flood actually completely took out one of the two water treatment plants in Nashville and was within 2 feet of taking out the other. So the city of Nashville was about this far away from losing all drinking water during this 2010 flood event. So we, as engineers, are first of all trying to locate new facilities outside the floodplain to the extent possible. We're a little bit fortunate at this facility that it's kind of slanted up on a hill, so we can move stuff away. There are energy costs associated with that. When you raise treatment infrastructure, you have to pump water up to that new infrastructure. That costs energy, costs money. It's easier to harden or raise critical infrastructure in new facilities than it is in existing facilities. But we're doing some architectural design that allows for further hardening in the future if deemed necessary. So there's platforms in front of some of the buildings in the floodplain that can be modified in the future to allow flood walls to be installed directly over top existing flood pathways. Another way that extreme precipitation affects water treatment is increased runoff, increased turbidity. Turbidity in water treatment is solids and stuff that's in the water supply. When you have surface runoff into a riverine or a system, you get lots of solids that get carried along with that runoff. And those solids have to be removed in the water treatment process. And that's often a key consideration for water treatment infrastructure. So surface water treatment plants are subject to increasing influent turbidity in extreme rainfall. At Omohundro, we had the ability to deepen our sedimentation basins and lengthen the plate settlers, which are what allow these solids to fall out by gravity. And that was it costs some money to deepen those basins, but the existing topography of Omohundro allows us to do that with relatively little cost. And so that's kind of a no-lose investment where typically we would design to what's considered the maximum historic solids loading rate. There's a maximum turbidity from some flood event in the past, and you design the treatment plant to operate under those conditions. We did that, and then we said, well, if we deepen our sedimentation basins for very, very little extra money, we can give them significantly better treatment during these high turbidity events by decreasing the loading rate on those sed basins. So lowering the gallons per minute that's flowing over those plates per square foot of plate area. And that's considered a no-lose investment, which is a great way to kind of get some of these climate change resilience built into new treatment facilities when you identify investments that can be made or changes that can be made that don't cost a significant amount. There's a significant data gap here, right? We designed this new facility not based on some future model of what turbidity might be in the future, but really on what was practical for the site. And that's because translating this increased precipitation, you can get increased precipitation from climate models. You can look at how does a 25-year storm event, how is that projected to change over time on a variety of different models. Taking that output and mapping it to stream flows in the river and increased turbidity in the river is a data gap. That information just doesn't exist. So it would be ideal to project what a future, maximum turbidity event might look like given the dynamics of the river. But that's not something that we're able to do right now. So instead, we look for these no-lose investments. Where can we increase treatment capacity at little cost to give them a little bit extra resilience for the future? Harmful algal blooms, taste and odor compounds, right? Cyanobacteria creates taste and odor compounds. Primarily, MIB and geosmin are two taste and odor compounds that are very prevalent in New York State waters. The city of Nashville recognized the need to install something at Omohundro to treat PFAS, right? PFAS is a big deal. You're talking about a water treatment plant that's going to operate decades into the future. The expectation is that that treatment plant at some point will need to deal with PFAS. So we tested a bunch of different PFAS treatment technologies. There's a couple of different ones that would have worked fairly well. We decided to go with granular activated carbon contactors because not only does granular activated carbon contactors reduce PFAS, here on the figure on top, we're using atrazine as a surrogate for PFAs and other compounds. You can see that it does an excellent job of removing atrazine, but it also reduces MIB and geosmin. It also reduces these compounds that we expect to see more and more of as climate change continues to affect this source water. So even though we don't have a great sense of how much the concentration of MIB and geosmin is going to change over time, we can still identify an area where we can select a solution that addresses an urgent need for the facility and also provides resilience to future climate change. Alejandro also has powder activated carbon feed system. They already see issues with algal blooms in their source water. So they have a powder activated carbon feed system to try to address that now. They're pretty reactive with that, right? The granular activated carbon is something that's always there, something that will always be able to address that. But since we don't really know how much climate change is going to affect MIB geosmin levels in their source water, we decided to keep their packed feed system in place. So if they're ever overrun by these taste and odor compounds, they have that there as a backup. There's no need to get rid of it, it's there. It might not be something that we would have invested money in had it not been there, but it was relatively effort to modernize that feed system and have it as a backup in case spray glass in case of emergency kind of thing. I think that was it. So wanted to give a quick overview of how the water treatment industry or water supply industry is trying to grapple with some of these challenges. Again, there's significant data gaps. So we try to look for these kind of, if I can go back to my beginning here, no lose investments, co-benefits, things that we can do to improve resilience in light of all of this uncertainty. And so with that, I think we're in decent shape. We have about 15-20 minutes for questions. So maybe the four of us can hang out over here and answer questions that the group has. Does that sound good? All right, awesome. Thank you. And I can go back and forth through slides if we want to do that. I don't know. Happy to take any questions if anyone has questions to start. Sir.
What is geosmin and what is MIB?
MIB and geosmin. MIB is short for a very long type of cyanobacteria whose name I'm not remembering off the top of my head.
That's your HAB connection, basically.
Yes, exactly. Yes. They are common products of harmful algal blooms. Yes, sorry for not making that clear.
Thank you.
Yes.
I was going to ask the same question, so thank you for asking that. I see that the focus with harmful algal blooms is on taste and odor. In our region, folks are mostly concerned about the cyanotoxins from the harmful algal blooms. So is that brought into the picture here as well when you're talking about your filtration systems?
Yeah. It's the taste and odor compounds, MIB and geosmin, are an easy way to test and measure the effectiveness of granular activated carbon or activated carbon in general. But yes, the activated carbon systems, both granular and powdered, will address the cyanotoxins as well. Thanks. Sir.
Wondering if there's any suggestion or rules of thumb to figure out how much is it worth to put in water retention systems and what scale for preventing flooding and for preparing for droughts.
Any thoughts?
I mean, so the question was value of water retention systems. One of the things I find kind of interesting is there's sometimes a hidden amount of infrastructure in the landscape. So there's places like in upstate New York, some of the largest flooding was 1972 during the remnants of Hurricane Agnes that came through. And mostly through USDA funding, they did a bunch of rural earthen dams. So if you're ever driving down to Corning between Ithaca and Route 13, you look over at some point, there's just big earthen dam just kind of sitting there. There's no water behind it. You might wonder what that was there for. But those sometimes activate and are useful. So, you know, I think the question is it's always a cost benefit. Should you do more of that and to have a benefit there? But there's certainly more of those structures in the landscape than you realize. Like Whitney Point, there's a dam there, and then also on the Genesee River, there's a dam there. So there's places where we've put in for infrastructure to prevent flooding that is definitely having benefits now, but we often don't think about it. And it's even interesting that you look at the USGS discharge records, you know, they sometimes have notes about changes in the hydrology, but they don't always note these massive dam structures that have been that have definitely changed what's going on in the record. So
In New York State, we have the old canal dams too, the feeders to the canal system.
and then you have all these small dams too. It's sort of, I don't know if people have really done this analysis, but do you have some like cumulative impact of having a bunch of small dams in your landscape? It probably does, but no one has ever said if you somehow took those away. But I think it's an interesting question. Like, could you construct a bunch of small dams, both for flood prevention and also possibly to supplement low flows and stuff?
Yeah, the beavers have their own ideas, but
I mean, they say if you were here 250 years ago, right, your landscapes, you would look totally different probably. In terms of what we think is a normal upstate New York landscape might be just totally different than we think.
just they're still there occasionally, the beavers, but the highway department usually doesn't like them.
There's sometimes efforts too now California's been doing this where the idea is to try to take those flood waters and to increase recharge to groundwater that's gone down during past droughts. And so the idea of like flooding certain lands during those times to try to increase groundwater recharge is another like active sort of research area that a number of people are working on.
Yeah, I'll just quickly add to that point that the application of like Furo has a lot of importance there because you can release the water more slowly into these recharge plains and actually have the desired kind of percolation effects.
Yeah, we've in the West Lake, we have the flats at the south end of Finger Lakes. A lot of them will be flat and filled in just because the way they're geologically formed, the sediments gather at the south ends. And that does help, and it's just wondering if we need to do more.
Yes,
I was just wondering if wetlands have any role in droughts.
Yeah, I mean, yes and no. I mean, they're certainly impacted by droughts, right? I mean, you know, a drier system, which can impact the form and function of those wetland systems, right? But in terms of like alleviating drought, I haven't really seen anything along those lines. I don't know if anyone else has anything on that, but I can't point to like work that's been done on that.
Really, I've seen anecdotally, like, I don't know, like National Geographic or reading about beaver dams, actually in particular out west. If you allow beavers to repopulate, the sort of hydrologic effects of increasing the groundwater capacity, or like basically the water table, can have some sort of important effects.
I'm gonna venture out there and say they probably do, because especially like it depends where you are. I think you can see storage in the subsurface and the geology. So I think in some places where you have like highly permeable geology, like limestone, like karstic formations, where you have big pore space, or like sandstone, you might actually get a lot of storage there. It might matter less. But I kind of think in upstate New York, where you have a lot of shales and like shallow soils, if you can add pockets of areas in upland creeks and things like that where you have wetlands, then it's just another spot to store water. It's sort of the same idea. If you put in a lot of ponds, if you put in a lot of wetlands or maintain the wetlands you have, it probably at the lowest flows, you might see something, right? It's not going to be like gushing water, but it might be the difference between having no water and a little bit of water in your stream during a really dry.
I will say often we run into issues when playing around with source water. Treatment infrastructure is often designed for a particular source, whether that's a surface reservoir or river. And if there's water quality differences in wetlands, you know, in certain wetlands, that might limit the availability or the ability for that to just be plugged into existing treatment infrastructure. but I think you're probably right, it can be used, it has to be. It has to be planned for in advance, it probably can't just be a, you know.
Yeah, I don't think there's anything magical about it, but I think it's just the idea of retaining natural spaces, especially in your upland areas. Anywhere you can do that to basically have pockets of places where you're storing some more water volume. You should have in the long term, as long as you can release that slowly, you should have more water in your streams during dry periods.
So I've got a question I'm way over here. But, and I probably not articulating exactly right, but on that notion of slowing the water down. And it may not be as applicable to, domestic potable water systems, but in terms of flood control, in my experience, something that really was a problem, especially now, and there's more climate change, is the increased intensity of storms followed by drought, vice versa. So in addition to those that are longer term with warmth and probably increased precipitation, is the dams. The actual, the dams are designed by Corps of Engineers people in a lot of cases, like particularly above floodplains. And out west, they get, where I was working in local government, they got a lot of really intense, like they could get the annual rainfall in 2 hours, a really intense storm. So they'll have many of those retention ponds and areas like New Orleans even has, with the new levees and everything behind it, so that they could feed water in there before it overflows and everything there. So is the maintenance of the dams, because of the intensity of the storms, is extremely important. And how to make sure that happens. Like where I was, these dams were maintained by ditch companies, irrigation companies. And this is under water law. So, Western water law has a whole pervasive oversight over everything that happens in water resources. So these dams would continually clog up, and they were dependent upon these irrigation companies. And this was in the Front Range of Colorado, in the north of Fort Collins. And so it was very difficult to make sure that those things got cleaned out. And if they did not, then we were going to get overwhelmed with it. And we were in the floodplain too, whether or not that was true or not, which is a whole nother issue about the National Floodplain Mapping Program and flood insurance and everything. But how do you factor that in models, whether these dams are continually cleaned out? I mean, I've noticed it in New Jersey, which is highly controlled, where they've got all kinds of retention areas, lots of dams, lots of drainage, really precise, requirements, and nothing going down into the culverts, and storm drainage and everything, much better than what you see up here. And it's still an issue with these intense storms. And right here in the city of Syracuse, the pseudo drainage system, combined sewer, is often clogged up. Often. So how do you factor that in and make sure that that's done? Like, and you're a consulting firm, so how are you making sure that that's done? Certainly by a water utility like Nashville, they probably have more robust approaches, but here it's a big problem. And that feeds into the whole CSO situation here.
Yeah, I think maintenance is obviously a huge concern across a wide range of infrastructure systems, right? And I think I forget who had the map of how old all the dams were, or how many of them were past kind of their age of operation. From a design,
Just keeping the filters clean.
Right.
It'd be new dams, they could be 10 years old, but
sure.
if those filters are not cleaned out regularly, then they're not gonna work. They could clog up very quickly.
Yeah, I will say from like a design standpoint, we have to assume a certain level of service that infrastructure systems are providing, and if they're not providing that, then there would be issues. We do have the ability to simulate that to a degree, depending on the model that we're using. But it's critical that these infrastructure systems are not just designed and built well, but maintained well. I don't know if you all have anything to add to that.
Use a seasonal forecasting, clean them up.
Well, there could be an application for that, right? If you know that there's storm coming, I think you're kind of getting at. Happened after storm events.
Would not clean their filters because they were lazy. I mean, I got sued by the city of Fort Collins. Our town got sued by the city of Fort Collins because we found out, luckily, one of the other employees forced me out there to go look at it. And we saw that this guy was not cleaning it out, and that was his supervisor. So for him to come to me, I had to reward him being a whistleblower. Basically, and then we got sued.
Yeah, the maintenance is often just as important as the design and operation.
It's a real problem.
Other questions? We have a couple minutes if anyone else has any thoughts.
Yeah, because one of the things that would make maybe the reservoirs and the upland ponds work better for the farmers is just integrating them into irrigation systems. Perhaps that might make it a little bit easier to use with the gravity flow, but it takes some design.
Are there any questions in the chat that we should talk about? Okay. Anything? Great. All right, well, thank you all. This has been great. Appreciate you all coming out and asking questions. We'll stick around for a minute or two if you have any other questions. Otherwise, I think we have about 15 minutes until posters start in the other room.
Yeah, see Mark, yeah, see you.